share your screen.
Okay.
Okay, everybody. Today we're delighted to host Fabio Capitano, who's from Monash University. Fortunately for us, he's dialing in from Europe, so he can be in almost the same sort of time area as we are. And he's going to tell us about some really interesting work he's been doing with Sue Smrekar, looking at aspects of Venus that appear to look similar to some aspects of Archean Earth. So Fabio, I'll let you take it away and tell us all about your exciting research.
Thank you very much, Michael. Thank you for the invitation. I would have loved to be in New York with you, but anyway, I'm a little closer respect to Australia. Let me minimize this one too. Okay, so in principle, the idea, oops. Oh, let me just, okay. That's embarrassing. Okay, sorry. Okay, I think my mobile phone decided to connect to my computer. Sorry about that. So, can you hear me?
Yes.
Yes.
Okay. So, my apologies for that. So, of course, getting to Venus and trying to understand how similar is this to the Earth, we have to define essentially, first of all, what we mean by similarities. So, what is similar to what? So, I'm going to take you through a process of understanding the way some aspects of the early Earth according to some recent work that I've done lately. So I'll have to review that. Otherwise, you will not be taken along. And then I'll take you eventually to Venus. So for those of you interested in Venus, this is going to happen at the end of the presentation. A little bit on my background. I am known for dedication to high performance computing. And I really like to use some fundamental fluid dynamics of the solid Earth and also solid dynamics, not only fluid dynamics, applied to our understanding of many problems related to plate tectonics and seismotectonics, as you can see here on the left, embedding observation from seismicity, new methodologies from AI, and some other work that I like to do on my own with some other colleagues that looks at evolution of planets and the tectonic regimes on these planets, and then planetary geoscience and early Earth, which is the work that I want to show you today. It's a work that I've done with some colleagues, Peter K. Wood and Oliver Nabel on the western side of the Pacific, and on the eastern side of the Pacific, they join me, Madeline Kerr, Dave Stegman at Scripps in San Diego, and Sue Smrekar in Pasadena. We've worked on this idea of tectonic regimes. The reason why is because the tectonic regime of a planet is strictly associated to evolution of its habitability. By this, we mean a number of processes that I will just touch upon in these slides. One of those is essentially the emergence of the atmosphere, so the outgassing of a planet and the formation of an atmosphere which is step-like and associated to some geological eras of the Earth that are a clear indication of geological features, of course, geological processes. That's how we divide the history of the Earth, but also associated with the record of the carbon and sulfur, which are evidence of life on this planet, and also the emergence of land and erosion. These processes also impact many other things. They interact with climate in many ways through topography, but also through the distribution of landmass and ocean sea gates, gateways and their closure. And in this called the Sepkoski curve, it's an ideal representation of how this interaction they led to the blooming of families of species on this planet, but also they might have caused their several extinctions indicated here with circles. So in few words, it all boils down to a very simple concept that we use in our understanding of our planet and other planets out there. So if we have plate tectonics, then possibly on Earth at least we have life, same on other planets, but if there is no trace of any plate tectonics at all, the condition for habitability they are not met, or at least they are not met in the way they are met on Earth. Possibly some other mechanism would take over in case. Another aspect that is quite interesting is not only whether this planet they do possess plate tectonics or not, but also how they became habitable. We understand this being the process through which the Earth went through. It's a long process, billion years process that took us essentially from the third stone from the sun to the blue planet. The record of all of these processes is kept in some pieces of the Earth that are called the cratons, which are the cores of the continents, are indicated here in red, and are the oldest, are the oldest. They are older than 2.5 gigayears. We have some other pieces of the crust and basements that are younger. So in any case, if you want to have a look at all these processes and the processes that characterize the early stages of the Earth, we have to go to some of these places that are indicated here in red. And this is something that we did. We went visiting the Pilbara craton. Cratons, as you can see here, they're not the most scenic places. That was my bed, essentially, for 14 days in the field. Summing up the information from a number of work that has been published throughout the years, mostly coming from cratons like the one that I showed you before, we have a number of evidences. The first evidence comes from xenolith, and the analysis of the juvenile basals is that in the early Earth, the melting was quite larger. It was up to 30%, 40%, or in fraction 0.3, 0.40 and above, which indicates that the mantle of the Earth was hotter. It was either hotter or more hydrated. We can't really tell, but in general, we have this range here, which is between 130 to 260 degrees more. Present day would be nothing more than 8-10% melting and temperature of the mantle current in present day. They are around this figure here. When we take all these basals and we plot them against age, we create this characteristic temperature of the mantle that implies that the mantle was hotter than present day, become even hotter around 3 gigayears ago, and then eventually decrease at around 50 to 100 degrees per gigayear. Oops. Another important information that we have is that this melting in the mantle occurred at a depth that range between 200 down to very, very, very shallow depth. Eventually, these xenoliths of the mantle, they're equilibrated at subsolidus temperature at depth that are even higher now. So it simply means that this material started melting 200 kilometers, went all the way up, and then eventually became cooler and came back down at where it is now, at the roots of the continents. The question, of course, this is the petrological record, which is 0D, ideally, and we have to put it in a context. The simplest way is to put it in the context of present-day tectonics. So how cratons form in a hotter Earth, we start with some ideas that are similar to those, some processes, contexts that we see in present day. I've numbered these. 1 to 3 are contexts for the formation of depleted continental lithospheric mantle and juvenile crust. And this can be perhaps a ridge or otherwise an island arc where we have some, flux melting through the mantle, or also a plume, the effect of a plume that creates a lot of melting, a lot of crust. Other processes are invoked to explain the stabilization, and these are subduction and stacking, or the thermal equilibration of these roots. When we look at all of these processes together in the same slide, of course, the question is this plate tectonics or not? These are all features that, except plumes, of course, that they belong to present-day plate tectonics. Well, the answer, a short answer is yes and no. So if we look at the field evidence, and this is field evidence from the Pilbara again, you can see that there is a long period of around 1 billion years in which we have evidence of horizontal and vertical tectonics. So we have some rifting, some little subduction going on with some arcs, but we also have some thick craton forming, possibly atop a plume, melting. So it's getting quite confused, the idea of something that can be plate tectonics or cannot be plate tectonics. Another aspect that is important, another question that arises is we have very little occurrences, very little outcrops of very old continents. And how representative are these of a regime that could have been global? Well, obviously the answer is definitely not. So we have to infer and try to understand whether this was the regime of the whole Earth or was just the regime of that 5% that is preserved to present day. Quite puzzling. It is puzzling, and we're not going to get out of it because this is equivalent to a known paradox in which we are looking at something and we have two ways to look at it. So either what you're looking at now, it's a heap, or otherwise to some others, it would be just a collection of grains of sand. Who is right? Both. Same with plate tectonics. So are we looking at a collection of plate tectonics-like features, or we're looking at a global interconnected regime that represents the whole planet? We cannot answer to that. We use some other ways to understand what a global regime of a planet could be under some specific conditions that are ideal for the early Earth. This figure you see here is a beautiful figure by Fabio Capitanio, but the work that is done in this field is essentially older, and I've taken one of the earliest one, the work by my fellow Australian countryman Craig O'Neill, with some other co-workers that I think they are listening now. So the evidence from the geodynamics is on not the features of tectonics that we observe in the fields, but on what could be a global regime. So the first one is the tectonic mode. We run models of mantle convection, and we understand that we can either form a thick lid on the top that stays there, and we call this a stagnant, or otherwise this lid on the top, which is a thermal boundary layer, can be broken and start convecting in the mantle like subduction, and we call this a mobile lid, or otherwise we can also be in a regime that is a little bit of both. It alternates. There's also some declination of that, some other environment in which we can have some of this environment some tectonic modes in the same regime or rapidly alternating in time. There's a number of different models with different names. I will not lead you through them because there are a lot, but the important thing is that each one of that, it represents an alternative regime. So we have a stagnant or sluggish lid, which is a proxy for the early Earth. Mobile lid is a proxy for plate tectonics, and then eventually an episodic one. So we have one regime, one tectonic mode. So at this point, there is another type of constraint, which is on the thermal evolution of the Earth. So if we take the simple regime that is a mobile, and we go back in time where the internal heating of the Earth was higher and the temperature was higher, we go through something that is known to be a thermal catastrophe. Meaning that the planet in plate tectonic mode will be so active, will release a lot of heat, and eventually this will imply that the mantle has lost a lot of heat in the last 1-2 billion years, therefore was incredibly hot. We don't have evidence for that. We've seen some melting degrees that reach 30%, 40%, but definitely not 100%. So the way we understand that, and we go back in time, is nothing else than a scaling analysis that puts together the Nusselt number and the Rayleigh number. And I put here some jargon for those of you that are not in the field. But the idea is that we do understand that the Earth was hotter in the past, but this simple propagation of the plate tectonic regimes implies that the Earth was too hot. So we have to rule it out unless we find some other ways to explain it. Another aspect that is implied in this is that the Rayleigh number also offers us a scaling for the thickness of the lithosphere by simply saying that in a hotter mantle, as you can see here, we would have ideally a thinner and thinner and thinner lithosphere. Well, it doesn't really perform well against the observation, which field from, evidence from the field tell us that we have cratons. And if you look at the whole thickness of the lithosphere, the continents back in time, in this work by Irina Artemieva, we see that when we go back in time, it's not true that the lithosphere was thinner, but the opposite was thicker. So we have the thickest lithosphere that is in the moment that the mantle was the hottest. So this is another paradoxical situation in which we understand each and every little part of this tiny animal, but we don't know what is the animal altogether, to the point that this platypus, back in those days, when it was brought from Australia back to England, it was considered a hoax. We don't consider geodynamics a hoax, but in any case, it's a relevant tool that we can use and adjust to understand a little bit better. So we isolate the key processes. We've seen that one of those is mantle convection, which is the way we understand geodynamics and the global regime. Mantle melting to form all the crust that we've seen forming in the continents, which is still preserved. And eventually a kind of a tectonics, a form of tectonics, which probably wasn't plain tectonics. So the way I've done it, I went back and I used a simplified two-dimensional Cartesian model of convection for the simple reason that many of the analytical scaling is done on these models. So why not? The details of the mantle convection are nothing fancy. Rayleigh number 10 to the 7, internal heat that varies, usual boundary conditions, plasticity law, which is what tell us whether the lithosphere can become mobile or not, and a range of yield strength that we modeled throughout the evolution of these models. Another key process that I just discussed is essentially the relevant amount of melt and depletion. So this is nothing else than the geotherm of ridge with a hotter mantle, and this will be the effect of latent heat, and the temperature along this adiabat will heat the solidus, and the solidus will create some melting. We can estimate in different ways the melting. We can estimate it for a dry mantle, the black line, for a wet mantle with the amount of water per volume here in dashed line. But we can also try to assess a little bit whether latent heat is important or not, according to the type of melting we like and the melt production we like to model, whether this is extracted or not. In any case, the difference is minor. And this is, so we end up with some degrees of melting that are quite in the range of what we observe. And in particular, we see this interesting, we can reproduce this interesting process, which is the melting along the adiabatic decompression of melt as it, of mantle, sorry, as it raises beneath a thin lithosphere. And eventually we create melt extraction and oceanic crust or basaltic crust in particular. The other part that is quite important to enable sorts of tectonics is that we need some temperature-dependent viscosity, common, but also we need to have a depletion-dependent viscosity or rheology in general. And this is the way I've implemented, which is following nothing else than Hirth and Kolstad, who shows that essentially if we have no melt, so just a geothermal ridge, the melting, but if we do not include the melt, we're going to have some viscosities that stay around a value. But if we add the effect of this depleted mantle, we parameterize in this way, so with simply a function of the depletion degree, which is this one, then simply we can implement in the numerical models a simple concept that is depletion, dehydration of the mantle. Dehydrated mantle is inherently more viscous, stiffer, and this is the viscosity we have. It's a simple concept that you can imagine that this is the geotherm of a thinning a thinning lithosphere, a thermal boundary layer. This is the temperature here. And this is the melting that increases, going from red to light blue, so a thick to a thin lithosphere. And if we do not include, we just use a thermal boundary layer, we ignore the effect of the melting, it simply means that the thinner is the lithosphere, the weaker is the lithosphere. On the other hand, if we add this effect of the dehydration of the mantle, the thinner is the lithosphere, the larger will be the melting, and the stronger it will be. We use a numerical code to solve, called underword, to solve the continuity equations and the constitutive laws. And eventually, this is what happens. This is a snapshot of a convective mantle. The convective mantle without plate tectonics, it's just convection at this point, creates some downwellings. The downwelling, they create a thinning of the lithosphere here, which is nothing else than a 2D version of the model that you see here on the right. And we have some thinning lithosphere, some rift on the top, thickening on the side. And here in white, we have a part of a mantle that is dehydrated and becomes stiffer. But because it's stiffer, it will deflect the flow around and will essentially push the deformation on the side. So we have this part here that is cooling now, and the thinning propagates laterally, and we create more melting and more depleted blocks. Fast forward, we essentially have this process propagating laterally. So we have a rifting. Rifting fails because we create a stiff mantle. Rifting migrates, fails again, migrates again, and keeps on migrating in this feedback that leads eventually to the suppression of the mobility and the stabilization of the whole lithosphere. Fast forward at the end of the model, these blocks eventually they become negatively buoyant and they start to converge together and they start to stack. So all these blocks that you see here are the blocks that you see down here. They start to stack one on top of the other. And eventually, when we compare it to the record of the xenolith that I showed you before, we can see that all of these blocks here that are numbered with Roman numerals, they cover the range of values that are reproduced by the constrained by the xenoliths. So we do a good job in reproducing the process we've seen at the very beginning, so the melting at shallow depth, and then eventually the equilibration at subsolidus temperatures at depth. If we play around with the plasticity, so yield stress, we have also some large-scale rifting in blue here. We have episodic subduction here, and crustal reworking somewhere else here. And these are all processes that have been inferred to occur in cratons, color-coded here, blue for rifting, orange for episodic subduction, and green for reworking. Most importantly, as you can see in this model here, the melting occurs, becomes very rigid lithosphere, and eventually allows to inhibit any tectonics at all, and stabilizes the craton, the lithosphere into a craton, and at the same time also preserves these features as fossil plate tectonics like features for eventually the geologist to be found. We play around with this lithospheric thinning that increases with the decrease in yield stress. But the important thing is that each one of these regime, whether it's a stagnant lead, episodic lead, mobile lead, they all end up with some similar features. I show here the velocity in the surface and the heat flow. But the main difference is that the degree of melting increases for mobile lead regimes, because mobile lead, meaning that the lead can yield, and by yielding can allow shallower melting. We go back to the record from the early Earth, and this is the record, shows depleted peridotite, which is the amount in percentage of mantle that has been, excuse me, depleted by severe melting. And we see three features in all of these strange names that are names of continental cratons. And we have three diagnostics. The first one is degree of melting, which is quite high. It's not indicated here, but I can tell you. The volumes of depleted continental lithospheric mantle, they are quite large, so up to 80% somewhere, and up to 20-40%, down to 24%, sorry. But also the depth of emplacement is quite interesting because most of these cratons, they show that the largest amount of melting is at very shallow depth. When we compare this with the models, and this is essentially the melting that you've seen, I'll show you. It's, okay. Oops, sorry. It's nothing else than the integral of this melting in the boundary layer. So what we observe that we have a large amount, a large degree of melting, and you can see here color-coded going up to, there you go, 0.3. So the blue, orange to blue, it's 0 to 30% or 0.3 in a fraction. The volumes are quite large. We get up to 90% of depleted mantle. And also the depth of the emplacement, it's very shallow. This occurs only if we prescribe the conditions for mobile lead. And as you can see, they're quite similar to these cratons here. We also have some other cratons, some other models reproduce some other cratons, but the comparison becomes too difficult and we leave it there. There you go. So the conclusion of this comparison is that cratons, in our understanding, formed under a mobile lead condition. And of course, some of you might be interested in saying, okay, but again, this is 5% of the surface of the Earth. How representative is this of a global regime? Speculation, of course. So big word. This is speculation in progress. We go back to the scaling of the Nusselt number and the Rayleigh number. And stability analysis implies that they scale with the power law with a beta exponent of 0.3. This has to be ruled out because, as I showed before, it would end up in a too hot Earth, and so we have to find something else. So scaling that was proposed by Jun Korenaga suggests that if we assume that the dehydration stiffening, which is this depletion of the mantle and the stiffening of the mantle through melting and extraction, there was constraining the laboratory experiments by Hirt and Korstedt, Greg Hirt and co-workers in general. So eventually finds a scaling that it's not the normal scaling, but goes the other way around. What does it mean? If you use classical scaling, by classical I mean the Jeff Davis classical, which now is adopted to be a classical. So there was the idea of a hotter planet would create a thinner lithosphere, this one in gray. But as I said before, if we assume that the hotter mantle creates a depleted mantle, then eventually the lithosphere can become thicker and thicker. It's a switch between what is known to be a thermal boundary layer, so monomineral mantle that becomes cold from the top, to another one that is thermo-chemical differentiated. So we don't have a thermal boundary layer or boundary layer formed by a cold mantle, but we have a cold mantle and cold depleted mantle. It's also a way to fix the problem of the internal of the increasing temperature of the Earth by just decreasing in time the heat flow that we measure on the surface. How this compares with the models? Well, these are my models and these are the scaling. So this is a classical thermal boundary layer and thermochemical boundary layer with this exponent that is positive or negative. And my models, these are models that are in a stagnant lead. So they evolve in time and they become hotter and hotter or cooler and cooler. And this is the way they evolve. So they tend to align to a thermal boundary layer for lower temperature, and they tend to align to negative beta factor for higher temperature. So they switch from one to the other. This is the thickness, average thickness of the lithosphere in my models. And this is similar to the scaling that was proposed in the past. All models, they show essentially that this is true. So if we use models that reproduce plate tectonics in present day here, these are the stagnant lead, but these are the plate tectonics. When we go back in time, plate tectonics model or mobile lead models with the square, they go back in time at a certain point. As I showed you before, the mobility is suppressed and there's no plate tectonics anymore, but we can have essentially these thick cratons forming. There's also a way to release the heat flow in these models that I haven't talked about, which is a differentiation in two domains. There is the solution Adrian Lenardic proposed, which is viable in our model. But I just want to show that another speculation in progress, that this inversion of the trend between heat flow, Q, and internal temperature of the mantle, if you want, it's something that was envisaged by scaling analysis by Adrian and Bill Moore, in which, of course, they suggest something similar. Mantle temperature, global heat flux didn't really go down all the way down from heat pipe or whatever, original to present day, but probably has had a couple of ups and downs that my models would ideally suggest. This is important because the same logic applies to other planets. But before I go ahead, I'd like you to give me a sign of that you're still there. Is anybody still there?
We're here.
Excellent. Okay, thank you very much. I had minimized the camera so I couldn't see you. So it's the same logic we use for other planets. And of course, why Venus? Because there's a number of features of this planet that are similar to the Earth, from work of Bob Stern with some additional, more or less the same size, same internal heat production, of course, according to a generic idea of BSE, so bulk silicate Earth. So many planets, all planets are formed in the same way or started in the same way. A Rayleigh number is more or less the same of the Earth. So of course, we can have a look at that. And it looks very different from the Earth. Has some striking features that are, as far as we can tell, topographic features. This is the best we can say. One of those that attracted my attention is the biggest of them all. In a very ambitious way, we tackled the biggest of them all. This is Ishtar Terra. It's quite big. It's as big as Australia, and has a flat land in the center, which is called the Lakshmi Planum. It's bordered by many other features that we'll have a look at. Some very elongated mountains that are quite tall on the side. There is a Maxwell Mountains up to 12 kilometers. It is a plateau that is as high as Tibet, and with some mountains around it as high as the Himalayas, size of Australia, as I said before, which is quite big anyway. And this is the view in this direction. Towards the east, and you can see essentially there are some lowlands here, some highlands here with the Lakshmi Planum, the flat at the center, mountains on the side. Processes that have been invoked to be relevant for the formation of these crustal plateaus were proposed by Hess and Parmentier. There are essentially the idea that to create a lot of crust, we need a lot of high mantle temperature that creates some decompression melting. And this ejection of extraction of melt can create a thickness of crust that are comparable to what we understand are the thickness on Mars. They must create also some depleted mantle layer by extracting. Melt fraction will go up and down in a similar way to what we've seen before, and the temperature of the interior of the planet will be ideally regulated. This, of course, was very an epiphany for me because it's not very different from what we think or what I just showed you we think is happened in the early Earth. Some form of crust, of tectonics is embedded in the crust. I will take it very brief, and this is a figure that I'm pretty sure is from the work of Jim Head, but I couldn't find, it's modified, I couldn't find the reference. There's a number of models, a review of models that they all invoke different type of mechanisms on the basis of some geophysical observables that I'll show you later on. In any case, there's a very broad range of upwelling in different ways with a plume or mantle upwelling, underplating, removal of the lithosphere, the root, some other downwelling that thicken the root, some sort of horizontal motion that would imply some subduction somewhere, possibly, or at least in the work of Adrian Lenardic, or otherwise this work by Romeo and Turcotte, the so-called pulsating continents, something that contracts episodically. So none of this is plate tectonics. There are some other models that are also even more complicated in a way, imply the formation of depleted mantle layers, the removal, a second formation, the congealing of a lava pond. So in general, we summarize this all and we say that the key processes that we observe on Venus, or we infer on Venus, are not that different from what we've seen before. Mantle convection, large mantle melting, some form of tectonics, but definitely not plate tectonics. Let me check the time. Yep. So, of course, at this point, we do the same procedure. We take our models of mantle convection with our understanding of mantle convection on Earth. We modify to reproduce the capture the condition on Venus, which are a slightly thicker upper mantle and a hotter surface up to 450 degrees Celsius. And we start mantle convection. The Rayleigh number there is 10 to the 7, which is ideal or possibly likely for Venus. And we embed also important to create, because there's a lot of melting, thick crust, juvenile crust, possibly juvenile crust on Venus, just like on early Earth. Eventually, we embed exactly the same process that you've seen before. This is what the model do. This is a Cartesian box that reproduces the upper mantle of Venus, and we start convection. You can see in the models here. You're all familiar with convection, I'm pretty sure. It's a ubiquitous process of the atmosphere, the hydrosphere, and the solid Earth, the mantle. Of course, on planets occurs on very longer time scales that you see here, 100 million years, 183 million years. This is a snapshot. So we do have these Rayleigh-Benard convective cells that form here with some downwelling and upwellings. In a cross-section you see here with a black line, which is this one here, you can see that somewhere we have the thinning of the lead. And where we have the thinning of the lead, which is somewhere here, we start to have these centers where we have the melting of the crust in the same way you've seen in the 2D models. The model keeps on going, and we still have a lot of melting forming, and eventually where we had the thinning of the melting, the trend reverts, and we have cooling and the migration of the formation on the side. This is nothing else. This is a cross-section in the section that I showed you before. It's not different from the models that I showed you before, but I'll illustrate some of the features. So melting here is in blue now. We have convective thinning with upwelling. The melting increases, reaches high degrees, 20%, 30%, 0.2 or 0.3 in fractions. This is the fraction here in blue, and in red this is temperature above solidus. Eventually what happens is that this part here, where we take the cross-section on the side, becomes, as we've seen before, becomes stiffer, cools, deflects the mantle flow and cools the lithosphere. And you can see eventually the red geotherm here, or venotherm, going below the solidus. At this point, we have that this depleted mantle becomes a cold root. We have temperature contours here in black, the depletion degree in blue, and the mantle flow in gray. But on top, I've plotted the topography. The topography here is a combination of what is sustained by mantle flow and also what is isostatically achieved. So the topography here, the elevation here, considers the effect of the mantle going up and down, but also the effect of the buoyancy of the crust itself. So what happens here that we have some topography associated with the emplacement of crust. And as this mantle flow is deflected on the side, we see that the central part subsides because it cools, but this migration of the formation on the sides makes such that there is some shortening occurring between this mantle flow moving laterally and the downwelling here. So we have this kind of a shortening that is in between the border of the plateau, forming plateau, and the crustal plateau, and then eventually the downwellings. And at a certain point, you can see that the migration of the deformation, and eventually we attain this shape that is more or less flat in the center and has this kind of rugged rims. We go back to the three-dimensional model, sorry, and we've seen the mantle convection at the bottom, and this is how the elevation looks from the surface. So Rayleigh-Bénard cells here, the center of the rifting of the lid, it's here, and we have these rims on the side. Then eventually it propagates laterally, and surprisingly starts off like a rift, but rather than proceeding as a rift with the central extension, the extension migrates laterally. Of course, this didn't happen in the model on the Earth because this is nothing else the effect of the only parameters that is different, which is the weakness of the lithosphere due to the increase in temperature. When we have a look at the topography, which is one of the evidence we have, Ishtar Terra at the radar looks like that. We have some tessera outside here, which are pre-deformed areas or the areas that were deformed previously. I probably have called this ridges, but probably is inappropriate. I'm pretty sure Sue will correct me on that. The central part is a planum, and all of these features are represented here. So we have some deformed areas outside. We have a flat area in the center. We also have some basins inside that are revealed by the georadar here, deep basins. There are also reproduced in our models, which doesn't have any cover of sediments, nothing, of course, the model. And also we have some features that look like very tall montes, so-called mountains here, very tall and very thin, rimming on the border of the plain. And we have the same. This is the elevation here in color-coded. So we have a high, thin mountain belts around this area with topographic features that are similar, and also the size. So this image on the right, it's the same scale of the Ishtar Terra. So we can reproduce something in the order of thousands of kilometers, which would not happen on Earth. The widest basin that I know of, it's rift at least, would be the Sirte Basin, 500 kilometers in Libya. When we compare all the other geophysical observables that we have, one of those is the gravity anomaly that we have from the Magellan mission. And the other one is the inferred crustal thickness that comes under the assumption that everything is isostatic. So the topography, we've seen this already. The characteristic is this coherence. So this match of or anticorrelation between the topography that is very high, the crustal thickness in green that is very thick here, taken from cross sections that are here along Ishtar Terra at the 30 west, and they are associated with the low in the gravitational anomaly, which implies that there is a buoyant root down there that pulls up a crustal, an area with the lithosphere with a crustal thickness, making it the crustal plateau. This feature is reproduced by our models. So we have some crustal thickness here that is in the same order of magnitude in green. Topography is quite similar. If we correct for a different type of crust, whether we assume this is basaltic or a bit more felsic, mafic or felsic, doesn't change that much. And we end up with an anomaly gravity that is anti-correlated. We underestimated a little bit the gravity anomaly, which is here in the order of 500. We have values that are lower. We've tried with an excess anomaly of 1.5. We would match it. This cannot be done, however, cannot be done because we have tight constraint on the melting, unless our understanding of the melting are different. So Earth and Venus would be different. But according others, or like the reviewer, or one of the reviewers of our paper, this is probably irrelevant as a little mismatch in the gravity. The most important thing is that we have the same anti-correlation. So at this point, we use the same mechanism, and seems like it works quite well for creating the creation or formation of cratons, and as well, works quite well also for the formation of this crustal plateau on Venus. Of course, at this point, the question is when a craton stops being a craton, starts to become a crustal plateau. So one of the parameters that are key to geodynamics is the yield stress. This yield stress, whether we assume that the lithosphere is hotter, like on Venus, or colder on Earth, the yield stress eventually encompasses the strength of the lithosphere. So low yield stress simply means that the lithosphere is weak, and high yield stress simply means that the lithosphere is stronger. Whether this is stronger because or weaker because of temperature or not, it's kind of an inference. So we can classify mantle convection with weak lithosphere or strong lithosphere. So when we have a very strong lithosphere, nothing happens. We are in a stagnant lead. Perhaps the planform are different because the lithosphere is hotter, because the surface is hotter on Venus. That would be the conditions you see here. But then eventually, when the yield stress becomes Earth-like, we can create some rifting with some melting that pulls up this crustal plateau. And I would say that these are more or less Earth-like conditions. And in this case, we create some cratons. But if we keep on weakening and weakening the lithosphere by just implying that the yield stress is lower and lower, then at that point, what happens is that rather than having this center here that they grow in this way, the rifting migrates laterally, as I showed you before, because the lithosphere is too weak to sustain rift. So the rift has to propagate laterally. And eventually we end up with the model at the bottom. There is the model that I showed you before. At this point, we are under Venus-like conditions. So apparently the stiffness or the yield strength or the rigidity of the lithosphere, however you want to put it in a way that there is a specific way to call it, but for this general audience, we will just call it a weaker lithosphere, is the key to create terra instead of cratons. So we have low lithospheric strength or hot planetary surface. What they mean, it's a matter of interpretation, and we infer a weaker lithosphere, which can be either high temperature also in the past. This model eventually they ran for 1 billion years, or otherwise could have been some water that has weakened the lithosphere in the first place. And of course, I'll have to warn you because this is nothing else than speculation again. I have more speculations for you. And one of those is how about evolution in time? Well, we really don't know. Seems like somewhere in the last billion year or so, dating on Venus is not really as accurate as it is on Earth. We started somehow in Venus with a very thin lithosphere where the deformation we observed was formed, and eventually the lithosphere became incredibly thick and rigid like it is in present day. Some strain rates have been inferred, and they are in the order of 10 to the minus 15 to the minus 16, around 10 to the minus 16 for Venus. So the models that I showed you before, if they have very high yield strength, they don't create anything interesting. There is no activity, no melting, so they simply do not reproduce anything that is nor Earth-like nor Venus-like. But as soon as we decrease the yield stress, we can reproduce an episode of strong deformation, which with the strain rates that are comparable to what we infer on Venus, and then eventually the strain rate would decay. A lot of melting will be created in that stage, and then eventually the lithosphere becomes thicker and stable. This is what the model show, and eventually reproduces a little bit the idea of a thickening lithosphere. Another question that is quite important, and I agree that it's a very delicate one. We're not talking about regime transition. The geodynamic regime is always the same, but a tectonic mode transition perhaps. So the question is, what would be the current tectonics then? Well, yes, the strain rates, they decrease, but nevertheless, if you can see this model through time, we start with mantle convection-like, then we have a strong activity with this deformation. In blue is the extension, and in red is the compression. At a certain point, we have downwellings and rifts. We can see that through time, eventually, all the rifts that have formed essentially the crustal plateau, they stabilize, whereas we still have some activity in areas that were dominated by downwelling, because downwelling are cold. They never achieve a lot of melting. They probably have some melting, but not enough. And eventually, at the end, we still have some centers that are associated, of course, with the local downwelling and upwellings, but also we have some features that look like linear features where we have localized minor rifting or compression. So we would have thin belts of compression and thickening. Again, this is
Fabio,
pure.
we only have about 8 more minutes, so could you try to wrap it up
Finish.
so we have time just for a couple of questions?
Yeah, I finished. So it's the
Thank you.
final speculation is that perhaps in the future we'll look at it, and perhaps this look like a little bit these features here. So very tall areas of volcanic activity with this chasmated, this rifts uh, propagating out of that. And I'll end here and I'll take some questions.
Okay, great, Fabio. Thank you for ending just on time. Unfortunately, Adrian had to run off, he said, to teach classes or something.
That's pity.
Excellent. So do we have any questions for Fabio? I guess I'm wondering if you know you made some I guess reasonable assumptions about which Rayleigh numbers you chose for your models, but if you changed that a little bit or and looked at differences in yield stress, do you think that that would make things fit a little bit better for the compensation curves you were a little bit concerned about, or do you think that's not a big deal and that, like the referee said, it doesn't matter so much?
That's a critical point because the constraints on the amount of crust, the thickness of the crust, it's used on Earth to scale for the potential temperature of the mantle. So this comes from McKenzie and Bickel in the 80s. So I'm not really in the position to say that Dan McKenzie was wrong.
Okay. Sounds good.
And I hope this is clear in the recording. Dan McKenzie was right. I haven't said anything against that. But yeah, that's the only point we have. If we observe 30 kilometers of crust, juvenile crust on the surface, this is equivalent to that much depletion. And the depletion against the fertile mantle give us that mass deficit, which is equivalent to a gravity signal.
Okay, great.
Any other question?
Like Joel's talking, but is not
Yeah,
unmuted. There he
yeah,
is.
sorry, I was. Fabio, you mentioned that the lithosphere in the past was thicker. No, it was thinner, and then became hotter. It will be thicker, right?
Yep. Yeah.
And that thickening it's because you have a crust, you have more melt.
You have the mantle melting, and the mantle melting eventually becomes stiffer, and it becomes the root.
Okay. So what do you think would be the reason why it was thinner in the past? Could that be the surface in Venus? Could be the surface more cold, more cooler?
Big question is the so-called resurfacing of Venus, which is not well constrained. So we understand that somewhere around 0.71 billion years, there was a resurfacing. We still debated whether it was complete or it was partial. Resurfacing, it's a big word. It can be either, some would say that the whole surface overturned, like a big subduction. Some others just say that didn't and was essentially obliterated by a volcanic event that has masked all the signal. The only thing that is quite reasonable is that it was thinner because it has a flexural response, which is frozen. So rheologically it was thinner. Now we think it's thicker, but not necessarily thicker. It's just more rigid. So whether it's thicker or same thickness, but it's more depleted, we still don't know, unfortunately.
Okay. And just maybe big speculation. Could that Venus had an ocean and some plate tectonics in the past before this?
Well, the resurfacing and thin lithosphere imply that, or a lot of melting that we do not observe anymore. A lot of melting on Earth happened 4.543 billion years ago, and we know that the mantle was hotter because the radiogenic heat was higher. But a lot of melting 1 billion years ago, so either a weak lithosphere to overturn, or a lot of melting implies that 1 billion years ago there was a lot of melting. So either a hotter mantle 1 billion years ago, which is a bit weird, or a lot of water. 1 billion years ago, which is also a bit non-Earth-like. Big questions. So either a lot of water, a lot of recycling. So perhaps for that episode, plate tectonics was viable, like on Earth, or otherwise an unusually hot mantle 1 billion years ago. But yes, these are the questions.
Could that been both?
Well, it depends to who you talk to.
Yeah, because if you have like, I know, yeah, Mike has been around this. Like, if you had some kind of leaps, some kind of gigantic mantle plume somehow forming in a plate tectonic world, what would be the consequences of that? I guess there's some work to be done.
Yes, yes. I'm not a big fan of large plumes because you cover the whole planet with juvenile crust, and you need a lot of plumes. We don't really see it. There are plumes, of course. I'm not saying that there are not, but plumes, they never made the continents on Earth, big continents. So yeah, how global can you go with plumes? Of course, they are there, but they contribute.
Yep.
And Fabio, one quick question. Do you think that surface temperatures could play some role as well? Because there are some theories that the surface temperatures on Venus could have been much higher in the past, maybe 1,000 Kelvin instead of 750 or even more. Would that play any role at all in your modeling efforts or not? And help you constrain things if that was true? Because, for example, we don't detect any crustal remnant magnetism on Venus. And one theory is that it's because the temperature was hotter and reached greater values in the Curie point of the materials or the magnetite. And that's why we don't detect any crustal magnetism. That's the only evidence for possible higher temperatures in the past. But do you think that would play any role if that was true?
It would. From a scaling analysis that Adrian proposed also, 450 degrees, they're enough to drop the yield stress by a factor 4. That's why I use the yield stress. So you can imagine that up to 1,000 would drop the strength of the lithosphere even more. And that could probably make the lithosphere suddenly so hot and so weak that it would overturn, or otherwise make it so thin that it could blast with an incredible amount of melting that we will never see on this planet. Of course, at that point, there are some hypotheses that the Venus was, or inferences, that the Venus was colder 1 billion years ago, the surface, or also was as hot as it is today, or was possibly hotter. But yeah, evidence should probably come from other fields like the one you mentioned. It would go well together with the idea of overturn or resurfacing by melting. So I wouldn't discard that. Can just not tell you whether it's a hotter surface, hotter mantle, or a more hydrated mantle.
Okay, great. I'm sorry, we have to wrap it up because we're getting kicked out of our room soon. But thank you so much, Fabio, and thank you everybody for joining us for this week's seminar.
It was good, Michael and Joao.
Yeah, thank you so
Nice
much.
to see you.
Thank you, Fabio.
Bye-bye. Hope to see you soon.
Okay, cheers, everybody.